Good evening to all. We'll start shortly, but I think on the dot 9 o'clock, I will give the speaker to speak perhaps. So I will just give a brief introduction maybe, because I missed it earlier. So welcome back to the last sessions of this inaugural of Malaysia. Yep. So if any of the participants have any questions, you can put it into the message. We can read it at the end of the talk from each speaker. Otherwise, at the end of the sessions, after the talk, you can unmute yourself and you can ask your questions. All right. I hope you have, those in Southeast Asia, I hope you have had your dinner, a good dinner, hopefully. Yeah. It's brilliant. Okay. See the time. All right, so today we have, these sessions, we have two brilliant speakers. Our first speaker is, I'm gonna take this challenge and see how I can pronounce his name perfectly. Athipat Thamrongthanyalak. Am I right? I hope so. So he's currently a member of the faculty at Chulalongkorn University, Bangkok in Thailand. So he has obtained his PhD in 2013 recently from UCLA under the supervision of Matthias Siemperner. His interest is in Tame structures, and he will be giving us a talk titled Tame Solutions for Linear Functional Equations. So off to you, Athipat.
Thank you for the introduction. So first, let me share my slides. Okay, yeah, just I think everyone can see it, right? Okay. Okay. So first, I would like to thank the organizer for having me here in this conference, or give me the opportunity to give this talk. And I would like to congratulate you on successfully founding this organization. Okay, so yeah, let's start then. Okay, so what I'm going to tell you about today is on this topic, Tame solution of linear functional equations. So the first part of this talk is going to be about the first word Tame. Okay, so let's see, what does this one mean? Actually, like if you attend yesterday talk, you probably have heard about this word already in Professor Wilkie talk, right? In his talk. Okay, so let me give you a bit of a recall then. Okay, so here we know that if you look at the real field, if you have the reals and then addition and multiplication, and you add the integers to it, then this structure is very wild, right? Because once you have addition and multiplication and on the integers, you have the ring of integers, then you can have the Godel coding, and you can do like so many things. You can have that, you can define all Borel sets in this structure. Okay, so that is pretty, the structure in model theoretically, this structure is not very, doesn't behave very nicely. Okay, so we're going to call this structure wild. Okay, on the other hand, we have this real field, right? Just real field itself. And we also know that when we consider the real exponential field, the real field with the exponential function, we know this structure is kind of tame, right? How do we consider that? And we can say that these two structures, they are O minimal, right? And what does O minimal mean? It means that we say that a structure is O minimal if every unarily definable set is a finite union of open intervals and points. And it's turned out that when you look at the geometries of definable sets in O minimal structures, it kind of have some connection with the concept that Grothendieck introduced. That is what we call the Tame topology program, that he trying to characterize like what type of topology should be considered as tame, right? And it's turned out that O minimality is like a good framework that fit perfectly with this concept. Okay, so that's another reason why we usually refer O minimality as tame structure. Okay, what else do we have? Actually, when we talk about the word tame, you can also think of it as, instead of as a word that describes the structure, we can also think of it as a word that describes a subset of R to the k. Okay, so let's say you have a subset E of some Euclidean space, right? And we would like to say, oh, this set, it is tame or it is not tame. How can we justify that? Okay, and one thing that we know, right? We know that the real field R plus and time. This is a very nice environment for the structures, right? Because yeah, as you can see, like the definable sets in here behave pretty nicely. So we can think of this as a tasting ground. So it's a tasting area that we would like to taste our objects. Okay. And what we're going to do in this case is, in order to determine whether a set E is tame or not, one way that we can do is, we have this environment. We're just gonna put that set E. We're just gonna put the set E into this environment, and let's see what's going to happen in these structures. Right, so when we put E in the structure, this is gonna become R plus times and E, right? And we're going to see like how these set E interact with everything in here. Okay, and we can see that if we look at the definable sets in here, and we found that the integers is defined in here. It also means that you can have, like, if it can define the integers, it can define everything that R plus times and Z define, right? It can define everything that we have over there, which means that it is somehow, it seems like it is even worse than the R plus time and Z. Okay, so in this case, we can think of this method as like a procedure that we can try to test whether a set is Y or not. Okay, so if it can define the integers, then we can say that, oh, that set must be very wild. Okay, even though like it doesn't look that wild in the very beginning, but once it can create something that is very complicated, we can refer to that set as wild as well. Okay, so what else can we do? We can look at the other extreme of this side. We can look at when R plus time and E is O minimal. We can say that once we put E into R plus time and get R plus time and E, and it's still O minimal, we can say that this set E is tame. Or you can say that E is definable in some O minimal structure, so it must be relatively tame. Okay, so that's the one thing that we can do in order to classify whether a set is tame or not. And so we have two extremes right now, right? Okay, so now let's see what do we have next. Okay, now there is a question that, so we have right now, we have two extremes. We have very wild set and we have very tame set. So the question that we have right now is there anything in between, right? Okay, so the next question is, how about the intermediate sets, right? Is there anything that is not that wild, not as wild as the integers, but not as tame as the O minimal sets, right? So that is a very interesting question to ask. Okay, now let's see. So the first thing that we would like to do is, we would like to know that, is this even make sense to ask, right? If every set is either O minimal or divided integers, then there is nothing to study here. So let's try to see, is there anything in between? Okay, so we can look at this set 2 to the z. 2 to the z is the set of 2 to the n, where n is an integer, right? Okay, so now you can see that when you look at this set is infinite and discrete. So it's if you look at it on the real line, it kind of, if you just consider the order, it's behaved pretty similar to the integers, right? But you may think that, oh, this one doesn't seem so nice. But when you look at it, right, as we already know, like the problem about the integer is when you have plus and times on the integer, where you have addition and multiplication on the integers. Okay, now when you look at it, if you think about it, it's not about how it order, but it's about like the ring structures on the integer that make it bad as well. Okay, so when you look at these 2 to the z, we also know that these 2 to the z cannot be written as a finite union of open sets, open intervals, or points, right? Therefore, this set is definitely not O minimal, right? So this one is not O minimal. But interestingly, we can also show that it does not define the integer as well. Actually, it satisfies the property that for every m that is in for every natural number m and a definable set A that is a subset of R to the m plus 1, you can find an n large enough such that for every x that is in Rm, the fiber AX is either has interior or is a finite union of n many discrete sets. Okay, so these this can be the same discrete set. It don't need to be distinct. Okay, so that's what we have. Actually, this property is like a generalization of the uniformity of in O minimal structures, right? Okay, but in that case, you can make this guy more specific. You can say like, oh, you can say something like, this is not n discrete set, but it is n singleton, something like that. Okay, so that's what we have here. And we can refer to structures that have this property, the minimal structures. And you can use the result from Miller and Tye, Chris Miller and Tye, in 2006 to show that this structure is it does not define the integer and it's the minimal. Okay. Actually, there are many, like something that behave like a sequence that you can add it to the real field, and it still does not create any integers. Okay, that does create the set of all integers. Okay, now let's see, what do we have right now? So right now we have something that define the integers, that is the y of this one. We have O minimality, and we now have the minimality, right? So we can also ask the same question that, oh, is there anything in between, right? So we can keep asking this kind of question. Yeah, and it's turned out that we can consider something that is Cantor-like. So if you consider the classic Cantor set, if you have that set, if you add that set into the real field, you can define the integers. But you can also create a set that a perfect set, a Cantor-like set that cannot define the integers. And definitely the Cantor-like set cannot be written as a finite union of open set and discrete set. So therefore this guy is not the minimal as well. And this construction was given by Hieronymi in 2015. So it's turned out that there are many different types of structures that we can consider that give different kind of tameness. Okay, and you can actually, this structure has a property that every unary definable set either has non-empty interior or is nowhere dense. Okay, so that's something that we have, right? Okay. Okay, so and when we talk about O-minimal structures, one thing that is nice about O-minimal structure is it have a very nice dimension theory. Okay, so let's talk a little bit about dimension of sets, right? So let's pi the let pi kd be the collection of the coordinates projections from r to the k to r to the d, and let E be a subset of R to the K. We can consider the following dimension. The dimension of E is the largest D such that there is a pi in pi, the projection from the R to the K to R to the D, such that the image of E under pi, it has non-empty interior in RD. Okay. So for example, you can think of it as, let's say you have something like a curve in R2, right? If you have a curve in R2, you can see that if you the curve in R2 has has no interior, so it's not this is not the one that you want yet. But if you project it down to the real line, you can see that you can get an open intervals, and that's one you have non-empty interior, right? So in this case, you can say that the curve in R2 has the graph of continuous function in R2 has dimension 1, for example. Okay, so that's what an example of set with dimension of a set. But actually, like when you consider dimension of a set, there are many different types of dimension that we can consider. Here is another type of dimension that we can have. We call this the Archward dimension of E. And okay, so so what does this one say? For each R that is greater than 0, we let NRE be the least number of open balls of radius R, of radius at most R that cover E, right? So let's say you have a set E here. NR sub E is you have a fixed radius of ball, and you're trying to count like what is the least number of ball that you need in order to cover these region E, right? Okay, so that's the NRE. And the Archward dimension is the infimum of the following set. It's the set of alpha, such that when you consider set of R over R to the alpha, and then NR, and then BR, this B capital RX intersect the ball of radius capital R intersect and E, and you move this ball of radius R like everywhere in your set, and then you keep changing the radius, these capital R, everywhere in your region, right? And you're trying to calculate like if you shrink the radius of the ball that we have here, right? What's going to happen? And yeah, and if you're trying to consider the infimum of R such that that make these sets bounded. Okay, so that's what we call the Archward dimension of the set E. And it's turned out that when you consider the dimension of a set E and the Archward dimension of a set E, you can get that the dimension of E must be less than or equal to the Archward dimension of the set E for closed set E. Okay, and it's turned out that we can use this dimension concept to talk something about the defining the integers on also. Okay, so in 2016, Hieronymi and Miller, they can show that when you have a set E that is a subset of R to the K, you can say that R plus time and E, it does not define the integer if I'm not going to go into details about what the metric dimension is, but we can say that the dimension that we define is an example of metric dimension, and Archward dimension is also a metric dimension. And we can have many kind of metric dimension, and we can it's turned out that Archward dimension is the one that's gonna give like the largest dimension among all of that. Okay, so the idea of how we can show this is we're gonna show that the largest one, if it doesn't define the integer, the largest dimension is gonna be less than or equal to the smallest one. The proof is difficult, so we're not gonna go into the technical details of this. But that's the a rough idea of what we need to get this one done. Okay, so it's turned out that yeah, besides what happened in R plus time in the universe and in a subset of the universe, right, can describe how tame your function, how tame your set is. You can also use the concept of dimension to say something about how tame your structure is as well, right? So you can say that in here you also can consider the contraposition of this statement, and it say that if r plus times and e define the integers, then you can have a closed set, right? Then you must have a closed set that you can define a closed set that gives different have different metric dimensions. Okay, so that's what we have from this theorem. And we can also look at the dimension theory, other aspects of mathematics on this one. We can look at this result from Tikhonovich in 2013. Tikhonovich showed that if you have a set E that is a subset of R to the K, and it is a D-dimensional C1 submanifold, and this set E is definable in R plus time and 2 to the Z, right? You can show that if the dimension of the frontier of E and the frontier of E is equal to the closure of E subtracted by the set E itself. Okay. Then we can have that if E has a finite D-dimensional Hausdorff measure. This whole if and only if the frontier, the dimension of the frontier of E is less than the dimension of E. So if the dimension, we take the frontier and the dimension drop in this structure, you can have that E must have a finite D-dimensional Hausdorff measure. Okay, and yeah, when I see this, it's kind of give me an idea, right? So we can see that when you talk about R plus time and 2 to the Z, it's an example of the minimal structure. So this gives rise to the question: does this one hold in every D minimal structures, right? Okay, and it's turned out that this is not true. Actually, even the weaker form of this one doesn't hold in every D minimal structures. So that gives me an idea of introducing this. We can think about what we call the measure theoretic tameness. We can consider a weaker form of this one. You can see that when we have a compact set, right? When you have a compact set E, definitely when you consider the frontier of E must be empty, right? So the dimension always drop in this case. Okay, so if you, so the question is, can we define a compact D-dimensional C1 submanifold that have infinite D-dimensional Hausdorff measure, right? So that's the condition that I'm looking for. And yeah, as a result, I can show that D-minimality does not imply this model theoretical tameness. The idea is I can construct a D-minimal structure. I can construct a D-minimal structure that this result does not hold, right? Okay, so the idea that we have right now is we can have O-minimality. That is right here. We have D-minimality. That is up here. We can have defined the integers, that is all the way up here. And we can also consider the model theoretic tameness. Model theoretic tameness, which is we know that every O-minimal structure satisfies this. The minimality is up here, right? Oh, so this is the tame one. So this one says something like does not define. does not define. This is the Tame. The concept of tameness. So we can have something like this. We don't know whether this one imply this one or not yet. But that's what we have. And we also have many other aspects of the tameness that I haven't mentioned about. We can talk about minimal open core. Have minimal open core, and so on. So we can have many different types of tameness that we can consider over the real. Okay, and the example of the minimal open set that is minimal open core is the set of the real algebraic numbers. Okay, so that's what we have here. And actually, like from the talk of Professor Yang yesterday, I think that this kind of concept, it's kind of give a very similar vibe as what we consider about the zoo, right? So, and the wording that we have, the tameness and the wilderness, is kind of matched with this word. So maybe next time I'm gonna call this concept as something that is in the zoo and something that is outside of this world. When we, let's say, for example, when we define the integer, right? This is in the wilderness side. Right? The object that is in the zoo is kind of tame. So it's kind of nice to see other people, like perspective of how we study things, right? Okay, so that's what I would like to talk about when we talk about the concept of tameness that we are working on right now. Okay, it's a little bit more than just minimality. So, but we hope we can find more minimal structures that is not known before. That would be nice as well. Okay, but we also want to know, like, can we classify other types of tameness as well? Okay, so yeah, that's what I have for the first half of this. And the other half of what I have is about the, when we have these different types of tameness, like, how can we know that it actually is tame, right? How can we, like, say that, oh, this guy is tame? Yeah, we need, like, supporting reason why. We need supporting evidence kind of to support it. And one way that I usually look at this is, if we can say that this structure is nice, it means that we are in the nice environment. Can we get a result, right? Can we get a result that also guarantee that, oh, this is nice? Can we get, does working in this nice environment implies that we can get some nice result in maybe different contexts or something like that. So what another part of my interest in this program is, can we have applications of working in this nice environment, especially to analysis problems and so on. So that's what I would like to do. Okay, and for this talk, in order to make it fit in this 15 minutes period, so we're gonna pick one topic that I'm gonna present it to you, and yeah, this is the one that I would like to tell you about. Let's consider this type of question on the linear equations. So when we talk about linear equation, usually you're gonna think about the matrix A, and and B, right? This is a m by n matrix, and you have the solution. This is m by 1 matrix, right? And the solution of this linear equation is these n by 1 matrix, right? Okay, so if you have that the entries of A and B, there are real numbers, you can use linear algebra to give you the answers, right? Okay, now the question get more challenging when you consider something else as an entries of A and B and Y. Okay, so what we would like to do is we would like to consider this equation, but when we consider the entries of A and B and also Y, they are not just real number. They are continuous functions from Rk to R, right? So these A and B, there are matrices whose entry are from Rk to R, a continuous function from Rk to R. Okay, and we can say that our set Y, Y is a solution for this equation dagger if Y is a continuous function that satisfy this linear equation, this system of linear equation. For every input x1 up to xk in R to the k. Okay, so that is the type of question that we are going to study in next. Okay, and for this type of question, it's turned out that the hard part of sorry, not yet. And the question that we asked is, so how to determine whether when you have this system of linear equation, does it have a solution or not? And yeah, how can we determine whether there is a solution or not? Right. So this is very natural question to ask. And just to make this one simpler, we're going to consider just one equation. But actually, this is where the hardest part of the study lies in. Okay, so this is the hard part of this one. Okay, so we rewrite this question a little bit to just consider about this one linear functional equation. Okay, so that's what we have. And people in analysis also interested about these, the second question as well, which say that if you know that if f g1 up to gn, they are well behaved in some sense, okay, is it possible to find a solution that is also well behaved? So what does this one mean? You can think about the word well behaved just like if you have f g1 up to gn, there are smooth function. Can you find a solution that's also smooth? Or if it's Cm, can you find something that is like the solution that is Ck for some k that is less than or equal to m, but it's not too small or something like that. There are many different versions of this that you can ask. You can think about the algebraic version as well. You can think about, if you have a function f g1 up to gn that is a polynomial, that there are polynomials, how bad can it be for the solution of this one? So this is a very natural questions that people ask, right? But it's kind of fit with the concept that I just told you about, that if we start with something nice, we should get something nice as well. Okay, so that's what we have for this question. And to make you more familiar with this one and see where the problems of this question come in, you can see that if you have a G1 up to Gn that has no common zero, this question is easy. So you can always find a solution of this one by looking at FGI and then divided by the sum of Gj, where j is equal from 1 to n squared. Okay, so when you consider this by I and you plug it in, if you have if Gi have no common zeros, you can make sure that what you have here is a continuous function, and that's going to solve the question. Okay, so that's what we have. So the real question lies in when the case that when you have a G1 up to Gn, they have common zeros. So that's where the hard part is. And just, okay, I have about 20 minutes. Okay, just to give you some idea, actually these C infinity variance of this question is also related to what we call the Whitney extension problems, and that's where it get me interested in this question, in the linear functional equation question in the first place. Okay, so let's see. So now how can we determine whether this equation has a solution or not? So there are many mathematicians who trying to solve this question. And in 2013, Pfefferman and Charles Pfefferman and Janusz Koller, they use a technique that is called the Glacier Refinement, which is a simplified version of what a main mechanics that Pfefferman used to solve the Whitney extension problem. And what we, okay, so he used this Glacier Refinement and Michael's selection theorem, which is another nice result from topology. We can use this to provide a necessary and sufficient condition to answer question 1. Okay, so this is a very nice result. In addition to the answer to question 1, Pfefferman and Koller also look at the following question. So if you have the question 2, when the condition that we are interested in is when f up to fg1 up to gn, there are semi-algebraic function. Okay, and it's turned out that if you have that fg1 up to gn, they are all semi-algebraic and continuous. And you know that the solution, the equation dagger that we have here also has a solution. We can find a solution, right? So the first solution that we have, it can be anything, right? As long as it's a solution, that's fine. But once we know that the function f and g1 up to gn, all the coefficients in our linear equation, linear functional equation, there are semi-algebraic, you can also find a solution that is also semi-algebraic. Okay, this is a very nice result, and they use algebraic geometries technique to solve it, which is very interesting. Okay, but when I look at this question, and we can see that, oh, I see this word semi-algebraic, right? Yeah, that is a very nice word for us to study in the concept of the tameness. Why is that? Let's first consider what do we mean by semi-algebraic set. Semi-algebraic set is a subset of R2 which is a finite Boolean combination of set that is the zero, and that is a zero of a polynomials over R, or it is the set of gx greater than 0 when gx is a polynomials over R as well, over R. And it's turned out that when you consider this word semi-algebraic, it is the same thing as definable in the real field, R plus time and R plus n time, right? So these give rise to the first question that we have. Can we do it for all O minimal structure? Right? Okay, so let's say like, can we do it for every O minimal structure? Can we change from the word like, oh, this is semi-algebraic, and then change it to, yeah, it is definable in this structure, that is also defined in the same structure, has a solution that is definable in the same structure. Okay, so we can consider at the other extreme. So we can consider that if you add R plus times and all these F, G1 and Gn, and it turned out that the structure define the integers, right? Since we know that every structure that define the integers can also define all Borel set, right? Yeah, okay. So it's defined all Borel sets, which means it's all defined all closed sets, right? And we know that a continuous function on R from R to the K to R, the graph of it is closed, right? So it can define the graph of every continuous function. So in this case, you can also say that, oh, yeah, this whole in general, and this whole when the structure define Z. Okay, now let's look at we know that if it's while, we can do it, right? Now let's see what we can do when our structure is Tame. Can we do it in the O minimal case? And it's turned out that when we have a structure that is O minimal, by the result of Matthias, Aschenbrenner, and I, in 2019, we can show that if f, g1 up to gn, they are all continuous function. And if we add this guy into r plus time, this one is O minimal. And we know that the equation stacker that we're interested in has a solution. Then you can also get that the equation Dagger also has a solution that is definable in R plus time f g1 up to gn. So we start with f g up to g1 and gn. We can get a solution that is definable in the same structure. Okay, so what does this one mean? It means that you can, if you know that the equation that you have has a solution, you can cook up the solution by using only symbols from here and logical symbols like equality and or not the axis for all. That's all you need, right? Or you can just say, oh, we only need the complement, projection, and union intersection, just a finite combination of that to create the solution, right? So you don't need something like infinitary argument to create that one. That's all you need. This is what you need. You can do it in finitely many steps, something like that. Okay, so that's what we have in the O minimal case. And it's turned out that, and this gave rise to the next question, what about the intermediate steps? right? If let's say if it's Definable, and so on. And it's turned out that for these questions, just for this question, we can have that if you have a structures, if you have a function f, g1 and up to gn that are continuous, and you know that the equation dagger has a solution, we can have something like the lower bound of complexities of the solution of it's not lower, it's just, we can find a solution of these equation dagger that is relatively tame, right? What does that mean is we can do pretty much the same thing what I just said here. You can cook up the solution of f and g1 up to gn of these linear functional equation that's generated by fg1 up to gn by using only finite combination of these guys, finite Boolean combination of these guys and projection. Don't forget projection. Okay. Yeah, that's what we can get from this question. Okay, so this, so and that is very nice because this doesn't depend on what f and gn up g1 up to gn are. You can always like get that the solution is definable in here. And this is a result that is proved by Thornset, Sokantika, and I in this year. It was published this year. Okay. And actually, like when we study this question, it kind of leads us to a very interesting question because we can study what we call the definable version of Michael's selection theorem. And let's say that if you have a function, a set value map T. So let me first go tell you briefly what the Michael's selection theorem is. If you have a set E that is a closed set, and you have T, which is a set value map, which means it function that map E to the power set of R to the N. Okay. Okay, so here you have this. Then we say that function y from E to R to the N is a selection of this set T if yx is in Tx for every x in E. Okay, or you can think of it as this selection of T is a choice function of this set value map T. So if we have no condition on this T, by the axiom of choice, you can know that if T of x is non-empty, then you can always get a selection, right? But that is not very interesting here. Since we are working over R to the N and R to the K, we can impose some, we can equip it with topology on R to the M and R to the K. And we can ask the following question, if can we have a solution that is also continuous, right? And the answer is no, right? So like, for example, you can think of this as a set value map from R to the power set of R, right? And this is each fiber is each fiber is the value of each point in your set value map. Okay. And yeah, definitely this one, you cannot have a choice that pick one element from each fiber continuously, right? So you need to have a jump in this one, for example. And similarly for this one, you need to have a jump from this one up here to this upper half up here. Okay, so yeah, this is nice because it means that this question is interesting. It's not that obvious, right? Yeah, so in order to make this one work, in order to guarantee that there is a solution, yeah, you need to have some condition on the set value map. And yeah, one condition that works is what we call the lower semi-continuous function. And since we don't have much time left, let me go through what Michael's selection theorem is. And by Michael's selection theorem, in which proved by Ernest Michael in 1956, he showed that if your set value map is lower semi-continuous, and you know that for each t of x is closed and convex. If it's closed and convex, then you can guarantee that T has a continuous selection. Oh, this is selection. I just selection. Okay, so here you can have a continuous selection. And it's turned out that we can also show this. These theorem also have a definable analog in omnimal structures. So if you have r plus time and t, this is omnimal, right? When you add t into r plus time, you get that this guy is omnimal. Then you can have a selection, a continuous selection that is also omnimal in the same structure. And if you consider E, that is a subset of R, and T is lower semi-continuous, and you can relax the condition on the connectedness, convexity into just connectedness, and you can guarantee that if R plus times and T is omnimal, then you can have that T has a continuous function, continuous selection, I keep saying function, continuous selection that is definable in R plus time and T. Okay, all right. And it's turned out that I can also show that it also holds in the minimal structure. And one of the key ingredient in the proof of the continuous solutions of linear equation that we have by Sokantika and I also need this Michael selection theorem. And here is the version that we have. We need to strengthen the condition on T a little bit in order to make the proof go through. So here we have that if T is lower semi-continuous and Tx is an affine subspace of R to the n for every x in E, then we have that T has a continuous solution that is definable in R plus time and T. Okay, so that's the key idea of the key ingredients that we need in order to get the result done. Okay, so let me skip through this a little bit and let me talk about let me end this talk with this theorem. Actually, what we did in that paper is more general than just working over the real field. Actually, we're working in the context that what we call an expansion of a real closed field. Okay, and we can show that if R, and we say that if R is an expansion of a real closed field R, we say that R is definably complete whenever for every unary definable set X in R, if X is bounded, then if X is bounded, then the supremum of X, if X is bounded above, then the supremum of X is in R, right? So that is this is the complete, it's an analog of the completeness of the real line, right? We call that this is definably complete structures. Okay, and yeah, definitely the real is an example of definably complete structures. The real field is an example of definably complete structures. Yeah, we can also think of the concept of tameness outside of the real as well. Okay, so that's what I would like to end it here. Okay, thank you so much.
Thank you, Athipat. Yeah. Any questions from the audience? You can unmute and ask some questions.
How many students or how many colleagues are you working with in Thailand?
How many students? Right now I have so Kantika, he's one of my students. He just graduated and he is working in Chiang Mai University right now. I have one PhD student. His name is Charuwat Panchong. I think he's here as well.
Oh.
Yeah, and I have one master student. Right now he's doing something else right now. Yeah, that's the student that I have.
How's the logic scene in Thailand? Are there many people working on logic?
Yeah, we are growing. Let's put it that way. So
nice. Yeah.
There are many Thai students who went study logic abroad, and they should come back pretty soon. So we're getting more colleagues in Thailand.
That's interesting. We should have more,
yeah,
interaction in the future.
I hope we can grow the community soon. I think I hope some of them in here. I invite some to this talk as well. I hope they might interested in this talk as in working in the logic. It's not necessarily mean like they need to. Yeah, I'm fine with having more logician colleagues.
That's true. That's true.
Yeah. Can I ask a question?
Sure. Hi, Marcus.
You had on one of the slides there was this question 1 about how to decide whether there is a selection. Is there you get information about this first question from your work?
This one?
There were 2 questions. The first one was how to decide whether such a linear equation has a solution.
Yeah.
And
this one, right?
Yes, right. Yes. So this first question is, well, I'm saying this because I've been talking with Shota about this in the past, and he has somehow tried to convince me, without me understanding this really, that this first question is actually the same as the second question. He said, if you can actually find out whether something has a semi-algebraic solution, provided it has some solution, some continuous solution. If you can find this out, then you can also decide whether it has a solution at all. That was something he believed strongly in. And so I was wondering if you also have
actually we have that if we can show that they are equivalent. You can show that if it has a semi-algebraic solution, then it has a solution. If the equate but do you mean that if f, g1 and gn are not semi-algebraic?
No, I mean all the given data are semi-algebraic, and I want to know, for example, in terms of the defining coefficients of the data, whether there is a solution to this system. And this is the way I interpret question 1. And then question 2, one could ask, if we are assuming it has a continuous solution, can we also produce a semi-algebraic solution? That's, I think, what you've been talking about mainly, right? But,
yeah. So if
it seems to be, I'm saying something that I actually don't understand, but it has been kind of conveyed to me that if you can answer the questions that you have now been answering, one can also answer question 1. I can't really give you evidence because I never believed this really, but it was, so I was just wondering if you can kind of make a conclusion now that you can also determine when such an equation has a solution.
Actually, there is a way that we can, I hope I don't go over time too much, but actually we can have a way to determine whether this one has a solution or not by consider, here you have this equation, right? G1, Y1, close up to Gn, Yn, right? Here, you can also think of it as if you plug in X to this one, and you think of all possible Y that satisfy this, it's a affine subspace of, let's say, R to the n, right? For each X, you get an affine subspace of R to the n.
Yeah.
Okay, which means you can think of this as a set value map. So you have Tx that send it to the set of all possible solutions of this one.
Right.
Okay, so you can convert this question into a set value maps question. And what you can do is you can use what we call the Glacier Refinement technique, the Definable technique, to trying to lean out the what we don't need. So we trying to cut the part that the solution that there is no way that it can create a continuous solution or semi-algebraic solution. We cut it out and get a new one. If it doesn't work, we do it more. We do it until it is stable, until we cannot reduce it anymore. And once we can show that, once we reach the stable state, then if the stable state is non-empty everywhere, then you can guarantee that it has a solution. That's roughly what we have. And we can show that it must reach the stable state at a finite state. We can know for sure that we can do that.
This is this Pfefferman Glacier refinement.
Right,
so
right.
Oh, okay. Oh.
Yeah, you can use Glacier refinement to do that.
Thank you.
All right. Thank you. We don't have enough time. Perhaps if you have more questions, you might want us to type it in, and then we can always forward it to Athipat. Yeah. So thank you so much, Athipat, for your talk. We have our next speaker, the last speaker. But before we invite our last speaker, I just want to remind everyone that we will have a photo sessions after the last speaker, the end of this session. So we will request you to later on to switch on your camera. So if you need to wear something nice, you still have about half an hour or so, but otherwise it's all right. It's just a screen.